I just realized today that that's where the title is from. It was in my brain, and I don't know where it came from. And I should have put the, the poster. Yeah.
Okay. So, yes, today's seminar is from GAUTAM, SATISHCHANDRAN, if I pronounce it well. So this topic is related to the seminar of Monday by Gedanken, which is a common work. GAUTAM just finished his PhD with Robert Wald and just moved to Princeton at the Gravity Initiative for a postdoc. When are you ready?
Okay, so thanks for the invitation. Thanks for the introduction. I really had a really nice time in Vienna. It's sad to leave tomorrow, but I'll leave you with this, I guess, and Dane can field any further questions people have while I'm gone. Okay, so the title of my talk is this provocative title, Black Holes Are Watching You. This is based on a essay I wrote with Dane and Bob for the, I should have written here, the Gravity Research Foundation essay competition or whatever. There is, I think we got third, but a more detailed analysis generalizing this, what I'll be describing today, to kind of all horizons in some sense, will come out fairly shortly, but let me explain to you today the simple case of the black hole and why they're watching you. And the way to frame this whole discussion, I think, is this thing that you guys are all familiar with, this kind of famous Chapel Hill conference, where I don't know if the YouTube people can see me. I tend to walk around too much for them to, we'll see. The camera's there. Okay, hopefully it's a wide angle. So this infamous Chapel Hill conference where the question of quantum gravity was something that was very debated. And many people had different ways of probing this question. Many of them were, from some ground-up principles. They were trying to probe it at that level. And Feynman had this kind of nice alternative approach, maybe kind of viewed as a top-down approach, where he really was thinking, if I want to understand properties of quantum gravity, one way of probing that is to consider Gedanken experiments in which the quantum theory and gravity both play an essential role. And by understanding, using principles of the quantum theory, we can then possibly infer properties about quantum gravity. Okay? And so one nice example, Dane presented on Monday, if you were at his talk, is this superposition of masses, which is now being promoted beyond even a Gedanken experiment to actual tabletop experiments. What I'll be talking about today is just a Gedanken experiment. This is not a proposal at the moment for an actual experiment, but in the spirit of Feynman, what we're going to show is that these Gedanken experiments, basically a generalization of what Dane was talking about on Monday, does really give deep insights into the nature of black holes and quantum gravity and its relationship to decoherence of quantum superpositions. Okay, so that's the idea. That's the very high-level motivation. I want to use these kinds of Gedanken experiments to probe aspects of black holes. Okay? So this is so black holes and decoherence are words that should be rightfully associated to each other in some sense. And black holes in some sense are well-known destroyers of quantum coherence. So as a very specific example, if you just have an entangled pair of particles and I just throw one member of the entangled pair into a black hole, well, this is a very dramatic and simple example of complete decoherence of the particle that I've kept outside, right? It's completely in a mixed state after I throw this other member of the entangled pair in. And so this is not so surprising. You can do much More with black holes, if you decide you want to start throwing things in, you could take a box of matter in some pure state. I throw it into the black hole, and we know by Hawking's calculation that the matter will emanate from the black hole and be entirely mixed. Whether it's mixed forever or mixed up to a page time is a matter of current debate, but the statement that black hole is spewing out this mixed radiation after you've collapsed all of the matter and any other pure state into the black hole is not debated at all, right? So you should really already be in the mode of thinking about black holes as engines of decoherence in this precise way, right? But what I'm going to explain today is that black holes are much more insidious destroyers of quantum coherence than you might have previously thought. So I'm not going to do anything as dramatic as what I just explained before. I'm not going to be even throwing any particles into the black hole or anything like that. What our main result is that if I put any quantum matter in a spatial superposition, the mere presence of a black hole in the vicinity of this spatial superposition destroys the coherence of the superposition in finite time. Okay? So that's the result. And at the risk of giving away the punchline, that's the exact punchline. And the way to maybe think about this, so if this is a cartoon, we'll have precise diagrams later in the talk. This is a cartoon. I have a black hole here. This is my matter that I've now put in a spatial superposition of two spatially separated states. And the statement that I'm making is that if I hold the spatial superposition outside a black hole, after a finite amount of time that we'll calculate, it'll be completely decohered. If I try to recombine the superposition, it will not be in an incoherent superposition. And the main mechanism is that the black hole acquires which path information via the long-range fields sourced by these superpositions. The black hole then inflicts a fundamental rate of decoherence on any quantum superposition in its exterior. And so what I didn't show in the picture I had before was that these spatial superpositions had, tied to them these long-range fields which register on the horizon of the black hole. And what we'll show is that that is exactly how the black hole is going to acquire which path information and destroy the superposition in finite time. Okay, so now this is enough cartoons. Let's do physics. Let's make this a precise experimental question. We consider a Gedanken experiment similar to the one discussed by Dane. If you weren't at Dane's talk, I'll be reviewing it. If you were at Dane's talk, you'll remember there was both an Alice and a Bob. I'm not going to consider Bob in this case. I'm just going to have an Alice. She's going to be performing the protocol, a similar protocol to the one that discussed by Dane, but I'll review it in the next slide. Okay. Okay, so just, black holes are complicated. I don't want to confuse anyone. Let's just go over the Gedanken experiment in flat space-time. Okay? So Alice Alice, the proverbial Alice, has a particle. So this does not have to be an elementary particle. Of course, it could be a nanoparticle. It just has spin. And I'm going to make it in a spatial superposition. I could use a Stern-Gerlach apparatus. I could use whatever modern-day techniques that one wants me to use. But I'm going to pass it, in this particular example, through a Stern-Gerlach apparatus to produce a 50-50 coherent spatial superposition. And the size of this superposition is of size d. And so for definiteness, let's just do the electromagnetic version where this particle has charge. We'll do the gravitational version at the very end, but I just don't want to.
The size of the superposition.
So the size meaning so I have one component of the superposition and the other, and I'm maintaining. By particle, I mean I only care about its center of mass, degrees of freedom, and the center of mass, degree of freedom, is separated by a distance d. Okay, so that I've made this is just getting you in the mood, hopefully, of thinking about spatial superpositions. This is the wave function of Alice's particle with spin up and to the left. This is the wave function of Alice's particle with spin down and to the right. And I've given you the formula for a superposition. So this is not so interesting right now. What's her protocol? Her protocol is that she's going to maintain this spatial superposition for some fixed amount of time t, capital T. And then after that time, she's then going to recombine her particle by passing it through a reversing Stern-Gerlach apparatus over some time scale tau. OK? And I'll show you a diagram afterwards so we can go over it again. So, and then she's going to measure the coherence of her particle. If her particle, in this example, is in a coherent superposition of spin up in the z direction and down in the z direction, she can measure the x spin. And if she ever sees down in the x direction, she's in an incoherent superposition. OK, this is, so I'm as Marius mentioned, my training is with Bob Wald. So I like to draw space-time diagrams whenever I get the chance. This is the space-time diagram of Minkowski space-time. I have null infinity here. That's where radiation makes it out to. Alice's lab and her particle go off to time-like infinity. And this is what I'm describing is the world line of the center of mass degrees of freedom of Alice's particle. So she's going to make a 50-50 coherent spatial superposition here of size d. As I mentioned before, she maintains it for some amount of time, capital T, and then she's going to recombine it over a time scale tau. OK. Do we all understand the setup of the problem? OK. What could be the cause of Alice's decoherence? Why am I even bothering to check the coherence of Alice's particle at this stage? Well, Alice's particle, in this example, I'm assuming Alice is a really good experimentalist and is going to account for everything else. In this example, Alice's particle is going to be decohered by the emission if she emits any electromagnetic radiation with which path information out to infinity. I'll give a calculation of exactly how to compute this, but that's how she's going to be decohered. When the superposition is static, she is not emitting any radiation. So only over this time scale tau is the time we have to worry about when she really has to, quote unquote, accelerate the superposition back together over this time tau, right? So she might radiate information over that time, but hopefully it's intuitively obvious that if she does this slowly enough, she will be able to achieve it. Go ahead.
Why aren't you worried also about the radiation emitted when you initially split the...
Yeah. Oh, good. Yeah. So yeah. Oh, I should have said that. I'm assuming that she's done that incredibly slowly, and I'm giving the free parameters of her experiment are this capital T and tau. That's just for simplicity. So yes, good. She could have ruined her experiment from the outset, as you were suggesting, which is that she could have, not slowly brought the superposition, made the superposition. Go ahead.
One thing that's confusing with these diagrams is that they're not on scale.
Oh yes, yeah. It's a conformal diagram. This is a PhD thesis, so just that part there. So yeah. Very good. OK, so that's the thing that I forgot to include is the radiation she might have emitted when she is recombining this particle, which is the only time that we really need to worry about in this process. OK, so how do we compute it? Well, what do? I catch all the radiation that makes it out to null infinity from this branch of the superposition and this branch of the superposition. I'll call those radiation states psi1 and psi2. That's the radiation that comes from Alice's path going to the left. And this is the radiation from Alice's path going to the right. And very simply, this should be a totally trivial statement, the decoherence is just determined by the orthogonality of the radiation from Alice's path going to the left and Alice's path going to the right. If she radiates which path information, it's calculated by the orthogonality of the radiation fields. So this is all in Alice's particle is the electromagnetic case. So this is all calculated in QED. Later, we'll calculate it in linearized quantum gravity. Yeah, so I'm treating Alice's, I'm treating Alice's particle as a effectively classical particle, like in the sense that, no, classical in the sense of the charge current doesn't have large fluctuations. In general, there will be correlations, but I'm neglecting the strong, basically I'm saying that Alice's charge current has very little quantum fluctuations in it, and therefore I can approximate it by a classical charge current, with an associated coherent state of radiation. That's what this is here. You're basically asking, you will definitely have, for the small amount of fluctuations in the charge current, you'll have fluctuations correlated in the electromagnetic field. That is not going to contribute a lot of which path information for Alice's particle. Oh, it does factorize here, which is where I'm calculating. I can talk about that later, but the key, it does, so this is a radiation state, pure radiation. There's no Coulombic degrees of freedom in this mode. Okay, so this, I should have mentioned, so I am relying a little bit on Dane's talk to do this to present this, but what I'm saying here is that I can collect the only thing you need to believe at this point is that I should be able to collect the radiation states here, and if I have which path information in the radiation field, I've decohered myself. And I'm collecting the radiation state here. Whether the validity of this formula, which is totally valid, is a statement about the Hilbert space factorization at time like infinity in Scry, which is true. It's because the Coulomb fields all collect at time like infinity, and the free radiation goes out to Scry. So you end up getting this factorization of the Hilbert space. This is an important point, but it was important also for Dane's talk, and I should have spent more time on it. So we can discuss afterwards if you want. But what I'm trying to express here is just if she radiates which path information, she's radiated, it's encoded in the orthogonality of the radiation fields that she emits. And this is a precise statement. Go ahead. Sure.
So at I plus, you have these two states, spin up and spin down.
Yeah.
So that's, do these states still contain any path information? Probably not.
No. Not in the Schrodinger, like in the wave function of the particle. Now they're all in the radiation field.
Right.
That's right.
So these are just spin up and spin down?
They're spin up and spin down. I said A1 and A2 just to denote where the paths came from, but they've recoalesced at time like at any time after this, after here. Yeah.
So strictly speaking, the state is not of that form you're saying now. Am I right? Because at that time they are already overlapping.
Oh, they are. I just said A1 and A2 to denote where these guys came from. But strictly speaking, if you just, you arrived, I guess, so her PhD was here, postdoc, so if you just arrived towards the end of her life, then you would not know where it came from. You would just see two wave functions coalesced and then, radiation with all the which path information. Okay, so good. So all I'm saying here is that, so I'm basically saying, I'm not trying to give a completely vacuous talk here, but the key point is, I'm being pedantic because we're going to have to be pedantic in the black hole case. If she recombines over a sufficiently long time scale, she should intuitively not emit much which path information. You can quantify this statement. If her time is much bigger than the effective dipole of her superposition, so she has some charge and some distance. If she closes this superposition slower than this time scale, then she can ensure that the radiation states, she radiates effectively nothing to Scry, and ensure that the decoherence is 0. Okay? So.
Turning into a question of which wavelength do you emit? Because if you merge them really slowly, then you emit a really long wavelength.
The wavelength is not important for decoherence. It's the number of photons you emit. So you're going to emit really, really low frequency photons, but you also emit very, very few of them if you satisfy this condition. Okay. So this is not going to be possible in the presence of a black hole. Yeah, yeah.
I mean, you said it's not important. It's really not important, or
It's not important.
But I mean, if the wavelength is much, much larger than the spatial separation, you're saying, nevertheless, there will be a number. I can just have to collect many, many of them, and then nevertheless, I will make them orthogonal. Is this
Yes.
what you're saying?
Yeah, yeah. I am saying that. Yeah.
Okay.
So, I mean, we are curious to why this is right. What we're suspecting is that it's two different things, right? We can get. So what he's in their calculation and the Marietal calculation, what counts is the number of photons. You do not see. Intuitively, you would expect this.
So it's very inefficient. It's not easy to produce very low wavelength photons. You have to take a long time to do it. So it's not like what ends up decohering you is the number of photons you have emitted.
It has to be relevant also the wavelength, because if the wavelength is really smaller than the spatial separation, then one is enough to decohere.
Well, if the way,
I mean, this is the Heisenberg microscope argument.
so I guess I'll give you an explicit formula towards the end, and we can talk about the formula and see if we agree. But yeah. So okay, good.
It's not just the number of photons, right? It's the difference.
Oh, it's the number of photons and the difference between the two states. That's right.
Photons to go from one
Yes, yes, yes. It's the number of photons that go from one to the other.
Like if they emit the same amount, if they emit exactly the same amount of the correct photon.
Yeah, it doesn't matter. Yeah, yeah, yeah.
This is what you do at
Okay. Thanks for the questions. Okay, so this is not going to be possible in the presence of a black hole. And no matter how slowly Alice does this, the recombination, this is going to be basically irrelevant, this part. All that's going to be important is this. Okay, so we now consider the analogous experiment. And now we have a bunch of complications. Because first, Alice has to, again, succeed in her experiment. I don't want her falling into the black hole. And I don't want to avoid any unnecessary radiation. So I don't want her to emit any unnecessary radiation. So she can achieve this first by attaching some rockets to her lab and maintaining some fixed distance away from the black hole. So she's going to make sure she doesn't fall in to the black hole. She also doesn't want to avoid any unnecessary radiation from her particle. So she's going to also have to apply some electric field to her particle or something, some force to a particle to maintain a static trajectory outside the particle. If the particle starts falling in towards the black hole, even in her lab, it'll start to radiate, even a little bit. And I want to do as ideal an experiment as possible and minimize as much radiation as I can. So her particle is going to follow a static trajectory outside the black hole, at least at this initial time, and then even after she creates the superposition, I'm going to make the two branches of the superposition follow stationary trajectories outside the black hole, static trajectories. Okay? So this is the diagram. So Alice is, again, a conformal diagram. But Alice is maintaining some fixed distance away from the black hole. This is the black hole. I know it's not the ones they show on Interstellar, but this is the horizon. This is the singularity. This is just to remember that this is a black hole. This plays no role in the talk whatsoever. Just the horizon is important for this discussion. She's maintaining some fixed distance from the black hole. She creates, so she'll have to accelerate very slowly her particle to new stationary trajectories displaced by a distance d. She maintains this distance for some amount of proper time in her lab, capital T. Then she recombines the particle over some time scale tau. So she's going to reaccelerate the branches of her superposition back together. And then she's recombined the particle at this point. And we just want to do the same calculation again. You can imagine her lab has some rockets and is staying outside the black hole. OK. Anyone confused about the setup? So first, we need to, if we want to be a lot more precise about this, we really need to understand how we calculate things on here. Because I need to calculate the radiation on here. So the first thing I need to do is tell you that when Alice recombines the particle, she could either now radiate out to null infinity or radiate into the horizon. Okay? So on either branch of the wave function, she could radiate out to null infinity or in the horizon, and we need to keep track of both degrees of freedom now. Right? And as before, Alice can avoid radiating to null infinity by following nearly stationary trajectories and quasi-statically recombining her particle as slowly as you like. But now we will show that regardless of how slowly she recombines the particle, she must radiate which path information into the black hole. So the statement here is that she can ensure, by keeping her timescales longer than any timescale present, the timescale due to this effect that I said before, but also now she has to move through some gravitational potential, which has a effective timescale of order m. She needs to make sure she's moving slower than that as well. So she really has to go quite slowly here. And then if she does this, the radiation out to null infinity is effectively nothing. She can ensure that she minimizes the radiation completely to null infinity. However, as we will see, she cannot minimize the radiation into the black hole. And what we're going to call this calculation is the decoherence due to the black hole, because, well, that's what it is. OK, so what is this calculation? Well, let's first talk about black hole geometry for just a second. This is just very simple stuff, not too complicated. So if this was unfamiliar to you, maybe you've seen this kind of diagram before, where a black hole is represented now. I've instead of straightening out the light cones, the light cone, the surface is now not a null surface, but represented by this guy here. It's still null, but I'm not representing it by a 45-degree line. That's what the black hole horizon is. The cross sections of the black hole horizon are spheres with metric, two-sphere metric q, and the time along the horizon is what people call affine time. It's related to the proper time in Alice's lab by basically a time dilation factor. Like, the time along the horizon is exponentially related to the time in Alice's lab. This is just, the natural time is affine time on the horizon, so that's what we'll be talking about. At the end of the talk, we'll translate everything back into parameters of Alice's lab. So just keep track of this v as effectively time along the horizon. And this radial coordinate is the orthogonal coordinate off the horizon.
So v is just limiting incoming
V is null geodesics along the horizon. It's right. It's view in the usual Kruskal diagram would be the one.
That's the outgoing time.
Yeah. So this is v along the horizon. Okay, and good. And so Alice is positioned somewhere, some radius away from the black hole. Okay, so let's forget the problem for a second and do a simpler problem. A much simpler problem, just purely classical, no quantum at all. Okay? So let's consider a warm-up problem of the radiation produced by just a charged body that I'm going to initially put at some distance r equals b, and then I'm going to just displace it to a new position, r equals b plus d, where this displacement is much smaller than the initial position of the initial distance from the black hole. Okay? This is a totally trivial problem. Let's just calculate it and see what we get. Okay? So this is the picture. I start with some particle at some initial position, r equals b. I slowly displace it to, as slowly as you like, or as quickly as you like, but that would be a bad experiment. But let's do it as slowly as you like to a new position, r equals b plus d, and let's calculate the radiation field that's on the black hole due to this process. And this is a fairly simple calculation. Maxwell's equations take a really simple form on the horizon. So what does this mean? Well, the radial component of Maxwell's field, the Maxwell field, corresponds to kind of the Coulombic information on the horizon. Okay? And what this is saying is that Maxwell's equations relates the Coulomb field on the horizon to horizon radiation, transverse modes. So this is modes basically propagating transversely that fall into the horizon. That's what this angular component of the electric field is. So what is this saying? Well, let's do the example. So if I have a static test charge, if Alice didn't displace this particle and just kept it at r equals b forever. Okay? Well, then a static test charge does not radiate any photons into the black hole, so EA is 0, and ER is just given by roughly the charge over the distance from the black hole squared. Okay, this is the obvious formulas that you would have expected, but I'm saying it is true, that a charged particle, static charged particle, does not radiate outside a black hole. However, now let's displace it. So now, throughout this process, if I displace it, I'm changing the size of this radial component of the Coulomb field on the horizon. It's not going to be Q over B because I'm now moving it to some new B. B equals B plus D now, right? So I'm changing the radial component of the Coulomb field. The time derivative of this change gives me horizon radiation, okay? And at this point, you shouldn't be very worried. If I make this very slow, if I change the Coulomb field on the horizon very, very, very slowly by slowly displacing this particle, you should expect the electric field produced on this horizon, the angular component, the photons emitted into the horizon, the electric field is very small. However, there's something you can't minimize, which is that in this process where Alice displaces the position of the particle, there's a permanent change in the radial component of the electric field from early to late times, which is given by this, the formula that you might have guessed. Well, if I integrate this equation, that means that the integral of the electric field over all time cannot be 0. Okay? So these are all just simple statements. So the electric field is very small, but the integral is given by the size of the displacement. So in terms of the vector potential, which is what we use to quantize in a moment, in terms of the vector potential, the electric field is given by the time derivative of the vector potential, which means that if I plug, this hardest calculation we'll do, we'll just take the time derivative, put it into this formula. This implies that the vector potential itself on the horizon must suffer a permanent change between early and late times due to the motion of this body if I take this body and displace it to a new position forever. Okay? So what am I saying? And at this point, you shouldn't be too worried. This is all very low energy processes. So I have a particle at some position B. If I slowly displace it to a new position B plus D, the vector potential must suffer this step between early and late times. The horizon registers a change in the vector potential between early and late times in this step.
So the whole process is spherically symmetric.
So if you do it slowly enough, this change,
What would happen if you separate
it's not
charges on a constant arc, on an arc or constant surface?
on an arc, angularly, you get you get a different effect. It's weaker because you're displacing it angularly, but the radial displacement is the strongest displacement. And there's no, this isn't spherically symmetric, right? Because it's strongest, yeah. So yeah, but I mean there is still an effect, is the point. Yeah. A is the angular. Oh, I should have mentioned. Sorry. My coordinates on the horizon are angular coordinates. So theta A basically is a variable that encodes theta and phi. That's all. So it's an angular coordinate on the horizon. The capital indices correspond to angular sphere indices on the horizon. That's all.
So the horizon is following the spheres.
Yes.
And V is giving you one sphere.
Each moment of V is a sphere. And what I'm saying here is the angular component of the electric field corresponds to the transverse radiation into the horizon that you lose if you turn it on at all. And the radial component basically corresponds to registering the Coulomb field on the horizon. Okay? And basically, changes in the Coulomb field even will give rise to radiation by this formula. You might not be so worried because if I do this very slowly, this is very, very small. But I'm saying that no matter how slowly you do it, the vector potential on the horizon, this is a gauge invariant statement to say that the change in the vector potential is non-zero. It's the integral of the electric field, so it's a gauge invariant statement, and it's saying that vector potential must suffer a permanent change due to the motion of this body. Okay?
What is the gauge invariant statement with respect to the vector potential?
a vector potential, you can gauge it, but the difference of the vector potential is gauge invariant. And all I'm saying is it's not zero and determined by the amount I displaced it. We're nearly done. So now all I need to know is how many photons are produced in this process. What does the radiation look like produced by this? And to compute the number of photons, I basically need to quantize the radiation on the horizon. Okay? And so I have a black hole. This black hole was formed by gravitational collapse. I need to choose a vacuum state. Nicely, Hawking showed us that the so-called Unruh vacuum, you don't need to know anything about quantization of radiation. I'm giving you the answer. But the statement is that for a black hole formed from gravitational collapse, the natural vacuum state was already given to us by Hawking in the 75. It's the so-called Unruh vacuum. And the Hilbert space of photons on the horizon just has the following norm. So you don't have to remember the norm at all. All you have to remember is that it depends on the Fourier transform of the vector potential, and it's an integral over these frequencies with this factor of omega here, and an integral over the sphere. Okay? So it's just a norm that you compute if you want to say that your particle belongs in this Hilbert space of states that comes from any black hole from gravitational collapse. Okay? And the only reason that's relevant is that for any coherent state, for any classical vector potential, the expected number of photons is determined by this norm. So I need to have picked a norm to calculate the number of photons. I need to pick a vacuum to tell you how many photons I have above it. So I picked this Unruh vacuum, because that's the one that comes from gravitational collapse, and you can then calculate the number of photons emitted in this process. And the only thing you need to remember is that it depends on the Fourier transform of the solution with this factor of omega there. And we're basically done with this process, because if I look at the Fourier transform of this solution, it must diverge like the Fourier transform of a step function at low frequencies. And therefore, it diverges like 1 over omega at low frequencies. The norm of that solution is logarithmically divergent at zero frequency. And as a result, this process, no matter how slowly you displace a particle outside a black hole, results in the emission of an infinite number of zero frequency photons into the black hole. These are what people call soft photons. Okay, so I just said it, I'll say it again. So displacing a charge, no matter how slowly, you don't emit anything to null infinity, but you emit an infinite number of photons. If you displacing a charge and keeping it there forever results in the emission of an infinite number of soft horizon photons. And this just due to the fact that the black hole registers the fact that you move the body outside. Okay? So if we don't displace over an infinite time, but we displace over a finite time and bring it back, n is finite. The number of photons emitted along this trajectory is finite, but large for large time. And so let's calculate it. It's
a weird thing.
It's a weird thing, I agree.
So if you don't move it, it's not emitting?
It's not emitting at all, no. But if you move it to a new trajectory, no matter how slowly you move it and you keep it there forever, you then you accumulate an infinite number of photons over the new trajectory. And let's see it in real time. So what am I doing is I'm displacing the particle to a new position. I'm irrevocably producing photons, a number of photons. If I kept it there forever, it would go on forever. But I'm going to bring it back down over some time, which is affine time v, which is proper time t in Alice's lab, basically. And the number of photons produced in this process, now I've given you all the constants, because we're going to do a calculation in a second, is dependent on the log. It's logarithmically divergent, so it has to be dependent on the log of the time on the horizon. But log of the time is proportional to the log of affine time is now, by this relation, linear in time. So what is the statement? You displace a particle outside a black hole. You are continuously at a constant rate emitting photons into the black hole. at this constant rate. The number of photons is constantly increasing. It's proportional to time. Okay. Oh, B is the distance from the black hole, the initial distance. D is the displaced, the amount that I've displaced. Okay, we're nearly done. So now let's go back to the Gedanken experiment that I mentioned before. But now let's do the simple case where Alice has two components, but she keeps one totally stationary forever. It never moves. And the other one follows this trajectory, that it goes off, gets displaced, and then comes back. We can do the general case, but this is just simpler to think about because I can give a talk and be done in 5 minutes or so. So now we're going to analyze Alice's full experiment. We're going to only displace one component of Alice's wave function, and we're not going to displace the other one. So the radiation, so again, we're doing it so slowly as to not emit any radiation to infinity. The radiation states are all on the horizon and only determined by the displaced trajectory. This other guy didn't do anything. He just sits there forever. Okay? So phi 1 is the corresponds to the state due to the displacement of the first component over a time t and then displaced back. The expected number of photons is exactly what we calculated in that one. And if you compute the the orthogonality of these states, the expected orthogonality of this coherent state of radiation inner product with the vacuum is determined by the exponential of the expected number of photons emitted. So if Alice emits an order 1 number of photons, then she is completely decohered by the black hole.
Does this assume that these n photons are independent from each other?
No. So what do you mean? Maybe I don't understand the question.
So you emit these n photons, and then you say, well, basically the overlap is exponential in n.
No, sorry. Whenever time I say n photons, I mean an expected number of photons. Expected number of photons. There's no state of definite photon number that I'm talking about. I'm saying that all the calculations are expected number of photons, which is all that's relevant for decoherence in this case.
Okay. So maybe just asking
Yeah.
to get this explanation.
Yeah. So it's just a statement of the inner product of two coherent states. In this particular case, if you have a coherent state and the vacuum, is determined by is exactly this formula. So it's the x. Yeah. So that's it. Yeah. Good. It's the magnitude of the inner product is this. There's a phase, of course, also, but we don't have to worry. But OK, good. So the decoherence is exactly this. If the black hole acquires an order 1 number of photons, which is infinite time, Alice's particle is completely decohered. OK. So why don't you have to worry about this for laboratory experiments? So in general, Alice's particle will be decohered. You make a quantum superposition and you hold it outside a black hole, as I hope I've shown to you today. Alice's particle will be decohered in finite time. This is a very slow rate. So in the electromagnetic case, if you have an electron superposed over a meter at some, if the sun was a black hole, so the mass of the black hole was the sun's mass, and we were doing this experiment on Earth, then this takes quite a while. However, if you did this experiment near the ISCO, so in the innermost stable orbit of the black hole, then and you shielded the lab and did all the right things, then this would be about 5 minutes. Okay? And in linearized quantum gravity, I'm not going to go over all the details in this particular case, but there's basically an analog of every single step of this calculation is the key point. The analog of the electric field turns out to be what's called the electric Weyl tensor. If the electric field was the time component of F, you take two time components of the Weyl tensor, and that's what the electric Weyl tensor is. And the angular components of the on the horizon of this Weyl tensor is the gravitational radiation. The radial component is kind of the Coulombic data, and in exactly the way as before, changes in the metric outside the horizon, changes in the radial component of the Weyl tensor of this Coulombic data implies permanent changes in the metric. and therefore a permanent displacement of a body, again, will give rise to an infinite number of now soft horizon gravitons. So the key point is, what you need to take away is there's an analog of every single step of this calculation in the gravitational case. There's no difference at all. So everywhere you could have just added an index, basically, in every step. Yeah, go ahead.
One question.
So this isn't linearized quantum gravity.
Yes,
by the way.
yes. It's not what the gravity was thinking. It's about already in the claims of the electromagnetic field. Because you assume that somehow in one of the components of the superposition of the charge, you assume that the electromagnetic field stays in the Unruh vacuum, which is the
Yes.
while in the other you get this.
So that's basically saying in that state, I don't change the radiation on the horizon. I don't change the radiation state. I clearly change the state, at time like infinity. It's a different state at time like infinity, but it's not a different state on the horizon. It's the same state, right? I mean, by making a particle, if I don't radiate anything into the horizon, it's not going to change the data on the horizon, like the radiation field on the horizon. It changed yeah, maybe, am I answering your, yeah.
Yeah, I'm not sure. Maybe that's the case. If that's the case with the calculation,
Yeah.
I still don't.
So there is a radial component of the electric field that's registered on the horizon. Maybe that's what you're worried about. But the data on the horizon that you quantize is the angular component, the transverse radiation. And I'm saying that's just 0 due to a stationary body. So that's like the Coulomb field that just propagates all the way to time like infinity and contributes to the quantization at time like infinity. But it has nothing to do with the quantization of the field on the horizon. But I am arguing that if you slowly displace and come back, then you activate these angular components on the horizon, and that is what kills you. I mean, that's what gives you the radiation. So that's the statement. Yeah.
Is it fair to say that we are not considering a sort of eternal black hole?
We are not considering an eternal black hole. No. If we were, I am not. That's because the Unruh vacuum is the vacuum of.
So let's say it's created by a null shell that is collapsing.
Yeah.
But where did this charge come from? Have you left it at the same spot since forever, right?
Oh yeah. I mean, if it got collided by the stuff and fell into the black hole, then there's no problem. Yeah.
Somehow, if you bring the charge from infinity, you would also expect to have some radiation because of that displacement. Right? What is very weird is why it's not radiating at all, on one position of the charge, and then you move it a bit, it starts radiating. I mean, how did the charge?
How did the charge get there?
Yeah.
Well, I mean, did you ask this question in flat space time? What's the difference?
We can wait enough time and assume that everything
Yeah. So if I have like a bunch,
But here there seems to be, which is I think what my responding out seems to be a contradiction because in flat space-time, you can displace, it will radiate, but at some point everything will settle.
No, but you could.
You displace, stop this displacement, you radiate something, but then you don't radiate anymore.
So I guess what I'm saying is like yeah.
So I think what he's saying is either the charge was there forever and there was some dust falling, but the charge was there forever, and then the dust collapsed into a black hole.
Yes, that's exactly the kind of situation.
Okay, but then I'm not sure that what you are going to get at that moment it will be Unruh state because the charge was there already.
No, you do. I mean, the calculation of the Unruh vacuum doesn't depend on the fact that there exists a
charge there.
no, you can have or maybe like you could have put it in a trap, right? I mean, there's no reason why let's.
Release the trap and then you change
No, you perturb the Unruh vacuum, but you don't perturb it on the horizon. That's the key point. You perturb the Unruh vacuum, so there's a different state of the field everywhere else, but you're not perturbing it on the horizon. So it doesn't contribute to any photons into the horizon. I mean, that's the statement. I mean, maybe I'm missing the question.
Yeah, what is weird is I think what you're saying is that it's very strange that a charge, when you move it and you keep it in a different position forever, just because, I mean, when when you start counting that this is at which point of the whole problem you start counting that this is the place where it does not radiate, what situation, what's the moment in the whole problem where that determines this is the point where the charge does not
Well,
radiate,
it's
and these other points it will radiate.
no, no.
It's a reference point where you say, okay, it's just a difference to the.
So if something comes by, like let's say Alice is trying to do this experiment, and I go ahead and kick it, it radiates. And I'm saying it's really easy to produce radiation, but in the most idealized situation, you still can't avoid emitting radiation. That's what I'm proving. I mean, if you can come by and you could not like my laboratory setup and decide you want to move my laboratory setup over to the left a little bit. And all I'm saying, if you do it in the presence of a black hole, you can't avoid radiating. It's yeah.
What is the situation? What is the physical condition that determines at which point the charge does not radiate?
If it stays stationary literally forever.
Stationary
Yeah.
forever, since ever.
Yes, forever. Yeah. So it's really easy. Yeah. If it's in the presence of, it has to be in causal contact with a black hole, obviously. But that's the only statement. If you're in causal contact with a black hole and you don't move, you're not radiating. If you move a little bit, you gotta radiate. It's a small amount. Maybe if you come back, you don't decohere. But if you don't emit a large number of photons, but there's absolutely no way to avoid emitting photons into a black hole. That's the statement.
So just a second. So we've stopped you at your before last slide. Let's leave him go to the last one.
Oh, okay.
And then we can have a discussion.
Yeah, sure. Okay, so the gravitational case is slower. If in this particular, you need to do pretty dramatic things. So, for example, if the sun was a black hole, but then you had the Earth occupied in a quantum state with its displaced over its center of mass, with its center of mass superposed over its own radius, then its superposition would decohere. Well, you need the whole Earth to do this in 10 microseconds. And let me just say, it's not easy to put the Earth into such a quantum superposition. So I think I said in the beginning, I'm not trying to make a proposal for an experiment in this regard. But let me just end with some other comments. So the punchline is, if you create a quantum spatial superposition in the presence of a black hole, the long-range fields of that superposition register on the horizon if you're in causal contact with a black hole. And these really truly affect the quantum state on the horizon. And what I'm showing is it's incredibly easy to radiate photons into the horizon due to long-range Coulomb fields. And as this results in a constant rate of production of entangling photons into the black hole, and after some time, you will be decohered. Your superposition will be decohered. In this manner, you should really think of the black hole as literally measuring or harvesting wish path information on quantum superpositions. And eventually it will decohere any superposition. You could wonder many things, like for example, what if I replace the black hole by a star? Do I get the same result? And the answer is no. This really depends on the existence of the horizon.
So is it kind of a nonlinear effect? I mean, the Schwarzschild radius or whatever comes in with some higher order, right? So it's kind of a nonlinear gravity effect.
No. Well, this is all in linearized quantum gravity. Maybe I'm missing the question, though.
I mean, if you say if you don't have a black hole, it doesn't appear. So if you just have a gravitating body, it doesn't appear at all.
Basically, all I'm saying is it doesn't depend on the local geometry that near you. It depends on you being in causal contact with a horizon versus the surface of a star. In the case of the surface of the star, you can recombine arbitrarily slowly and make sure and you don't emit any wish path information. But in the case of a horizon, the horizon really registers the change in the radial component of the vector potential, electric field, and results in true radiation into the horizon. That's gone forever. Okay, so this effect, there's a question. Oh, sorry.
So
Yeah.
this, the statement that there are infinitely many photons crossing the horizon is clearly an IR infrared.
Yes, that's right.
divergence that comes from the fact that these null generators just go on forever.
Yes.
all the way to yeah. So
Yes.
unbounded integral.
Right. So.
This isn't it by itself a strong assumption about the structure of the causal structure of space-time at the quantum level, because we don't know what happens to a black hole in a full quantum theory.
Yeah, so you shouldn't take too seriously the when I displace it and told you to stay there forever because the black hole will evaporate. Is that what you're saying? In finite time.
Well,
But I'm saying
we don't even know what happens to the inside, what is the causal structure of the entire space-time.
But you only need
whether there is unitarity or not.
Yeah. So in terms of there's a couple of points there. One is whether the horizon is a weak field regime. It's absolutely not a place where quantum gravity effects are important. You could
locally, but if you make an
assumption
about the entire causal structure, like all the null rays that generate the horizon, this is not anymore. This is now an infrared statement about the structure of the theory we don't know.
No, but I would not. The only reason for me to displace the particle and leave it there forever was to show you this infrared divergence. But the calculation of creating the superposition, closing it in finite time, does not depend on the what the future. I mean, I just need to be in causal contact with the black hole over that period of time. So the statement is a little. I'm not assuming, it would be very problematic if I required the black hole to be there forever because, as we know, black holes evaporate. The statement is that you have a black hole in your vicinity. You are displacing the field outside the black hole, and it's registered on the horizon. And then you can calculate the number of photons emitted into the black hole. But I'm not saying, and the time scale has to be less than the time scale of evaporation or even a page time. But all of those are like 10 to the 60 years for a solar mass black hole. And even for the electron in the superposition, and the sun was a black hole, that was 10 to the 40 years. So you'd have to wait 10 to the 20 more years, roughly longer, so a factor of 10 to the 20 to be able to even take into account any late time behavior of the horizon. Maybe I'm answering your question, or maybe I'm not. Yeah. So the technical point is that it's a.
If the black hole evaporates, there is necessarily.
It's not killing if it's evaporating.
Yeah. So if on any timescale in which the back reaction is important, this all happens on timescales much quicker than on timescales in which the back reaction on space-time is important. That's the statement. So the statement is that to the effect that you can describe the black hole horizon as me doing a straightforward Stern-Gerlach experiment outside of a fixed geometry of a black hole, you get this result. If you have any time scale under which the back reaction is important, like 10 to the 60 years, then I would not claim that I have the full calculation. I have a huge part of the calculation, but definitely not the full thing, because you have to take into account the fact that the black hole is evaporated. Go ahead.
I have a suggestion, because I feel for you. So you were in the last paragraph of the.
Oh yeah. What did I get to? Oh yeah.
I have to say, because I have a Zoom now.
And let me make a comment too there. People are very interested, but there's some things you're taking for granted, like timescales of evaporation and things like that, that you should explain.
Yeah.
Close your talk.
Okay, let me finish the talk and then I can take more questions then. Okay, right. So this we don't think is of practical importance to any contemplated current experiments, but we think it really is of fundamental importance in quantum gravity, in the sense that really we're showing that the way a black hole seems to act, and horizons in general, really seem to act as though they are watching you. And so let me just end there, and I'll take a lot more questions.
So if you have flat space-time and you put your experimental space in an accelerated
Yes, that's the, yeah, well, yeah. So there's a paper to appear where we generalize this effect to all killing horizons. So if Alice does the experiment in the vicinity of any killing horizon, so Rindler horizon, a cosmological horizon, she is just decohered at a constant rate, determined by the size of the superposition and the properties of the horizon. So, you know, in the cosmological case, the expansion of the universe.
Yeah, so I'm going back to this question of the wavelength again, because, okay, Minkowski maybe is not important, but I feel that here it might be important. So, namely, what happens for classical electromagnetic fields in some black hole spacetime, maybe, let's say, rotating black holes, maybe. Then, when you try to scatter, like, let's say, plain electromagnetic waves of rotating black holes, and you vary the frequency, what you see is that for some frequencies, the black hole is basically transparent for that.
And determined by the size of the black hole and also the parameters of the angular. Yeah, so one thing you could ask, even in the Schwarzschild case, so as I was discussing the Schwarzschild case, if I just try to impinge, like impinge a bunch of very low frequency radiation into the black hole, it would be very inefficient however, so the key thing was that this radiation was sourced. And I don't have a great answer for you right now, but it seems that in the case where you have Coulomb fields that are sourcing the radiation on the horizon, the black hole is incredibly efficient at absorbing those, regardless of how low frequency they are. The difference is basically the example that you were giving and the examples that people have studied is basically shining light or radiation into a black hole, and then yes, the absorption of the black hole is really but however, there's this constraint equation coming from Maxwell's equations that I highlighted before that says that any change in the radial component of the field, which is determined by sources in the exterior, sources horizon radiation into the black hole. And so in some sense, Coulomb fields generate or make it more efficient for the black hole to absorb radiation by that equation. I mean, that's the only interpretation I can give at the moment. Yeah.
This should be easily tested with some numerics, like doing like point sources with the Minkowski equation. That would be super easy.
Yes. Yeah.
One could test how much of the radiation falls to the horizon.
Right. So that's exactly right. Yeah. So, and I'm saying that if it's sourced a sourced Coulomb field that's generating the radiation, the black hole is extremely efficient at absorbing it by that equation that I gave. Yes.
So I think we'll be going back to the equation that we had. So my point is, if I have a cloud of gas, basically this is still like Minkowski spacetime, I have some charge somewhere at some point, that collapses, forms a black hole.
Sure.
I have then you tell me that what is left, the structure of the vacuum nearby the horizon, is the same or unassuming. Is supervacuum.
Yeah.
What the evolution, taking into account that during all the collapse evolution there was a charge.
Yes.
Is it still?
Yes.
Okay, then I understand.
Okay.
I'm not sure
Yeah.
of this,
No, it is.
yeah.
The statement of the Unruh vacuum locally on the horizon is a local, like you can just set up data on the horizon, and it is the Unruh vacuum on the horizon. Maybe I can explain in a lot more detail, but I'd have to,
I'm familiar with this one, but I thought that it was a solution in the case of a free field outside without any other extra source.
But it's important that I'm not putting the source through the horizon. If I do, then you change it. But if I keep the field outside, the field on the horizon is source free and Unruh, and is the Unruh vacuum.
It does not affect.
It doesn't affect it.
So where do you use the killing horizon property to derive this quality?
Yeah, that's a good question. There's a few places it's used. One is the statement of the vacuum state. The vacuum state for us was a state that's invariant under the stationary killing field. So that was one place it's used. The other statement is that, in general, if you have a horizon and, well, I think there's like a Hawking rigidity theorem that says that if you have a horizon and you have a stationary, and it's, you know, stationary space-time and a horizon, it's a killing horizon. So you don't have a lot of choices on what kind of structure you have, and you pick this vacuum state. Another place we use this is Maxwell's equations take a very simple form on the horizon. Yeah. I don't know of an analog statement like this for if you just, well, it's certainly not true on an arbitrary null surface that you get this nice equation. Yeah.
Good, I see. And so, other than that, you're not coupling the electromagnetic field to the metric, right?
Yeah, so it's a test charge in the, it's not significantly back reacting on the space-time.
So you have a electromagnetic field on top of the space-time.
Yes, yes.
And if it's a killing horizon, you get that relation
Yes.
on the horizon.
On the horizon, yeah.
I see. And you interpret this, interpretation of this is that the coherent derivative on the left is
Oh, I should have said, this is the angular derivative. I should have mentioned that, yeah. This is all transverse. Yeah, and so this is like changes in Coulomb field on the horizon, which is very easy to do, generate horizon radiation.
how do you see it's outgoing?
Oh, it's out. Well, it's ingoing into the black hole, but that's because of the time derivative of the radial component corresponds to, well, it's the angular component just corresponds to the fact that it's transverse, but it's future directed, so it has to go through the horizon. Yeah, that's all. So the angular component is just telling you which components are generating the radiation, which is transverse to the horizon, and it has to be spatial.
Okay, how do you get particle creation of the future infinity for this?
Particle creation, like in the Hawking calculation, or?
Is this what you're saying, that you get that's what you're saying, you get an expected number of photons at square plus, right?
No, on the horizon. So what I'm saying here is that you have the horizon, you have the radial component, the radial direction, and then the horizon. Well, this is a two-sphere, and I'm saying that it's only have so many directions. So the transverse directions of motion are the angular components, and what I'm saying here is that if you have radial component and then a weaker field, let's say at late times, that generates transverse motion of the electric field, which falls into the horizon. And this can all be done in such a manner that the electric field at here is 0, or as small as you want, and no photons are emitted at scry. Nothing is emitted at scry in this whole process. That's why I call it no, not even soft. Not even soft photons are emitted in this process.
Because just the fact that the electric field vanishes doesn't mean that
Yes, well, as I used in the other case, yeah. But you don't get a soft photon contribution in this process. There are processes Alice could do in her lab to emit soft radiation to scry. That's, I guess, in our follow-up, or in a different follow-up paper. But in this case, it's really due to the presence of the black hole. You're trying to minimize all your radiation to scry, and you still get this result.